Good afternoon, everyone. My name is Feng. I'm currently affiliated to Siemens Corporate Technology, but this work was actually done when I was in Imperial College London, and this work is joint work with Singapore University of Technology and Design. Sorry, how to move to next? First, I would like to give some background on industrial control systems. As the name indicates, industrial control systems are a combination of software and hardware to monitor and control industrial processes. Such kind of systems are usually found in some critical infrastructures like power, grids, gas pipelines, and water distribution plants. And in the past, such kind of systems are usually designed in a standalone way, which means they are isolated with other networks and systems and keeping in an air-gapped environment. But now, with the trend of IoT, such kind of systems are becoming more and more connected to the internet. And on one hand, this evolution has significantly enhanced the operational efficiency and reduced the maintenance costs of this kind of systems. But on the other hand, from security lens, such evolution can also lead to some new cybersecurity threats. And unlike conventional IT systems, a security breach in such systems can cause very significant results. For example, damage to very important national equipment, such as nuclear facilities and massive power outage of power grids. And this is a typical architecture of industrial control systems. It consists of 3 layers. In the bottom is the physical layer, where there are field devices such as sensors and actuators to monitor and control the physical process. And in the control layer, it will receive the measurements from the sensors and issue commands to the actuators to perform actual physical change. For example, turn on or off a pump. And then in the top is the supervisory control layer, where there are some higher level monitoring and control functions such as human-machine interface and also some anomaly detection or intrusion detection systems are deployed. There are some existing anomaly detection mechanisms which are specifically designed for ICS. For example, the device-based where it usually uses the idea of device fingerprinting to detect intrusive devices. And also there are program-based mechanisms where they discover anomalous behavior by actually checking the code or the data flow in the programs on the PLCs. And there are also network-based mechanisms where people reveal anomalies by checking the network traffic, and such as the header, payload, timing, and the sequence of messages in the ICS network to find anomalies. And the focus of our work is the process-based mechanism, where we look directly at the physical process variables such as sensor readings and actuator states and their mathematical relationship to identify anomalies. We think process-based anomaly detection is very important because this is where the actual physical change can happen, physical damage can happen. So a commonly used process-based anomaly detection method is to rely on a predictive model, such as autoregressive model, a linear dynamic state space model, or even a recurrent neural network. And use the model, the idea is to construct a model based on previous sensor measurements and actuator states to predict the next sensor measurements and compare it with the observed value. And this, if the residual error is larger than a specific threshold, it will raise the alarm. But we found that in practice, in many cases, it is very hard to define such a decision boundary to separate normal and abnormal sensor measurements. And also this kind of method is also very vulnerable to stealthy attacks where the attacker can inject malicious deviation of sensor measurements in a very in each step in a very small value. And so our work is to propose a new process-based detection method based on invariant rules. So what are invariant rules? Invariant rules are just some physical conditions that must be satisfied for any state of an ICS, and they are generally defined by system engineers during the design phase of the system. And for example, in the right hand of the there is a design graph of water tank. There are two level indicator transmitters, two valves, and one pump. And from this graph, the system engineer can derive two invariant rules. The first one means that if the level indicator 101 is high, then the valve 101 must be open. And the second says that it is more complicated. It says that the level indicator 301 is low, and the level indicator 101 is high, and the valve 201 is open, then the pump 101 should be open, should be on. So here comes the question: can we learn such rules not just by a manual process, but learn it from data? So yeah. So the answer is yes. But before we introduce how to learn those invariant rules, I first want to give a definition of invariant rules. So assume that we have a time series data log collected from ICS, and in each signal there are two vectors, one for the sensor measurements and one for the actuator states. And we also assume that there are a set of predicates where we call items, and each signal satisfies a subset of the predicates in I. Then we can call this signal as an item set. So this is just an assumption. Later I will introduce how we generate those predicates set. And then we can formally define an invariant rule as this one. So basically it says that if the item sets if we think the item set in the left hand, then the item set in the right hand must also be satisfied. So here's an example which said there are two predicates that are satisfied in the left hand side. Then there are two other predicates must be satisfied in the right hand side. So how can we learn such kind of invariant rules? So we decompose this learning process into two steps. The first step is predicate generation, where we generate a set of meaningful predicates from the data log to construct the predicate set I. And the second step is to mine invariant rules. And because with the predicate set, we can transform the data log to a database of item sets. Then we can mine meaningful invariant rules just from this data set. how we do predicate generation for discrete variables, which usually represent actuator states. It's a very simple problem. Just emulate all the possible states. For example, for a pump actuator, we can generate the predicates that indicates the pump is on and the pump is off. And for continuous variables, which usually represent sensor measurements, and we propose two strategies which utilize the dynamic of control systems to generate predicates. The first one is called the distribution strategy. The second one is called the event-driven strategy. The distribution strategy basically assumes that there are some hidden control states to govern the update of sensor readings at each timestamp, and we drive predicates based on which hidden control states a sensor updates occurs. And the second, the event-driven strategy assumes that the update of actuator states are triggered by reaching some critical values of sensor measurements, and we derive those predicates based on the pre- and post condition of those event triggers. So how do we define the distribution-driven strategy? So assume that we have K hidden control states to govern the update of sensor measurement. Then we assume that there is an expected update under this hidden control state, and it is associated with Gaussian noise. Then we can feed to infer all the hidden control states for a sensor mesh update. We can feed a Gaussian mixture model for all the updates of the sensor in the data log to capture all the distributions of all the underlying hidden control states. And then we can also decide how many hidden control states are there by criteria such as minimizing the Bayesian information score. And after we have inferred all the hidden control states, we can generate the predicates based on which hidden control state this sensor update belongs. For event-driven strategies, we first need to define what are events. So we define events as discrete changes on actuator states. For example, an event can be a pump is switched from on to off. And to find the event trigger for this event, we can first define all the time points at the data log where this event occurs, and then we feed a lasso regression model for all the values of sensor measurements at all the timestamps when the event occurs. And then if we find that our predicted sensor measurements and the real and the observed sensor measurements, the distance is very small, than a very small threshold for all the timestamps in the event. When the event occurs, then we think that an event trigger for that event is found. Then we can generate predicates based on this event, the pre-condition and the post-condition of this event. So using these strategies, we can transform the data log to a database of item sets. Then we can define meaningful environment rules. The meaningful environment only need to satisfy two conditions: minimal support condition and the non-redundant condition. Minimal support condition is just to let the event rule has some significant statistical significance. And then we can use actually association mining to mine all the event rules from the database. It's just a very simple problem. Then I will talk about our experiments. So we have two experiments based on two data sets from water distribution testbed and water treatment plant. And the data set is split to the training set and testing set, and we inject some attacks in the testing set, and we compare performance with the invariant rules designed by system engineer and a residual error-based model. And we use 3 basic metrics: true positive rate, false positive rate, and normalize the true positive rate for all attacks. And also PK is means that we think that this attack type is discoverable by our method if the true positive rate of this type attack is larger than k times of the false positive rate. Then we find that our data-driven invariant rules can achieve much better performance than the residual error-based model at the same acceptable false positive rate, which is represented by tau e here. And our data-driven invariant rules can also have better performance than the design-based invariant rules. This is also similar for the SWOT testbed. So some reasons why our method is better. So one reason is our method is more robust to sensor noise, which can effectively reduce false positive rate. For example, we have 2 similar invariant rules, one for design-based, one for data-driven, but our data-driven rules can cause 0 false positive because it can take into account of the noise. The second reason is our data-driven. We can generate a much larger set of invariant rules than the design-based. And the third is the data-driven invariant rules can span several stages of the ICS other than the design-based rules. And also we have compared there are some pros and cons compared with the residual error-based method. If you are interested, you can talk with me later. And so the conclusion, invariant rules can be automatically learned from ICS catalog with a combination of several machine learning and data mining technologies. And using data-driven invariant rules can achieve better results. And some possible extensions, we can add nonlinear predicates and sequential invariant rules to our current work. Thanks.
Very short question, maybe? Okay, I have one question.
Okay.
What type of attackers does your system not prevent? Like, are there any limitations of this invariant modeling?
Oh yeah, I think the most important reason why our model cannot detect some attacks is because all the predicates in our system are linear predicates. So if there's some very highly nonlinear relation between them, so our current method cannot capture it currently.
Okay, let's thank the speaker again.